So let's see. We've got the reaction we left off with last time, which involved halogenation of two butenes there. And let's go through that. So we'll begin with that. And what we've got is bromination of the trans 2-butene. We go through the bromonium ion. We'll have to review that a little bit. But you can see the anti-addition of the two bromides, right? And if you rotate around this bond right there, you can see that this molecule is what? It's got a mirror plane relationship. In fact, it has a center of symmetry right here as well. So what do we say? This is achiral. This is a meso compound. Okay. Yeah. Achiral. And it's because of the trans stereochemistry here, and then the anti-addition from the bromonium ion, and then backside opening by bromide to give that product. Now, if we start with the cis alkene here, we'll get the same anti-addition of the two bromides. So you picture bromonium ion, and then bromide adding from the bottom. That will pop this open to this. You see we lack a mirror plane now. In fact, if you rotate around here, you can see both bromides are up or down. Let's see, what are the stereo centers here? This is R. We'll also generate SS, okay? But regardless, this is chiral. And it will generate an equal amount of the R enantiomer and the SS, so we'd say this is DL. Okay. So what does this bromonium ion look like again? Well, it's got the bromide bridging, and it's got the plus charge here. And so bromide anion adds from below and pops that open like that. So it'll give this stereochemistry down right there. You see the two methyl groups are across from each other, so that keeps track of it. Now the difference one here with the cis, the bromonium ion, is bridging both of them, and the two methyl groups are cis, and then bromide adding from the bottom, and then opening up, that will get that product right there. And you see we can analyze that. That's indeed chiral. We could have attacked the other carbon over here on this side. And notice that would have given us the SS, the other enantiomer of that. So those are those two examples there. Maybe one to elaborate a little bit here. If we treat this with one equivalent of T-butoxide, say sodium T-butoxide, just one equivalent. We've got this hydrogen right here, which is anti-periplanar to the bromide right there. And let's go ahead and pull that hydrogen off and have the bromide come off. And what will form here? We'll have the two methyl groups cis to each other and that bromide right there, okay? But if we do this one here, we've got that hydrogen down, and if we have T-butoxide going there, you see the two methyls will be trans to each other, and the bromide that's left will be right there. Now there's a homework problem like this for chapter 10. So hopefully you can work on that. I think it's problem number 67, where instead of two methyls here, you have two phenyl groups there, okay? So the thing to recognize here is bromonium ion forms from the initial attack of the alkene on the bromine molecule, and this holds for chlorine as well. So it'll give the bridging bromonium ion, and then backside attack inverts that stereocenter and gives the trans product. Normally you see that. It's also trans here from the cis alkene. It's the same mechanism, but because the geometry of the alkene starting with, you see, carries through there. All right, let's look at the next reaction, which is the Halohydrin reaction. So this is reaction number 4. If you're keeping track here, I think we've numbered these. So Halohydrin. Okay. And the key thing here is we're going to do the same thing with halogen, but instead of having an inert solvent with nothing else in there, now we have water as a nucleophile. So what's going to occur here? Well, we're going to generate the same chloride, but there's no chloride minus to function as a nucleophile here. Water is going to be the nucleophile, and we're going to end up with this. So this is why it's called halohydrin. Hydrin's another name for alcohol. You could call this the halo alcohol reaction there. And it's going to give that trans relationship from the trans alkene there. Let's look at the mechanism. Let's go ahead and attack here. We'll get chloride top and bottom, and remember it's plus charged. Chloride minus is our byproduct at that point, and then water is going to attack from the bottom and bring that up, and that will give us what? Hydronium ion and chloride up. Okay, are we done there? No. Water's in excess. It's a solvent in this case, so it's got a huge excess, so we can use another water molecule here to grab the proton off there and form that. Yes, it does become acidic. Hydronium ion will start to form. You can watch the pH of this reaction actually go down and become acidic. But that's halohydrin. Let's look at some other examples of it. So if you've got cyclic alkene, let's see, you've got cyclohexene, chlorine, and water. So those are the reagents for halohydrin: chlorine, water, or bromine water, and you're going to go to the halo alcohol. Okay, and what's going to be our product? It's going to be chloride up or down, and then the alcohol opposite. Okay. Now, what about the stereocenters there? Yes, those are two stereocenters. Chloronium ion can be blocking the top, and we could attack with water on either side. So we're going to get what? A racemic mixture of that chiral molecule. Okay. Let's see. How about this example? Let's have bromine now, water. Now, where is the water going to attack? Now it's not symmetric, right? So let's look at this. We've got bromonium ion, Br, and don't forget about bromide minus, it's there. But we've got water. Now water can attack either here or here. But what kind of a nucleophile is water? It's neutral, right? So it's going to wait for ionization to occur. So we're going to get what? Especially in this case, what type of carbocation is that? It's tertiary. So water is going to attack there, and we're going to get this product, bromide and the alcohol right there. Okay, the tertiary alcohol. So in general, we've been talking about the electrophile, which is bromine in this case, goes to the N carbon, the less substituted carbon, and the nucleophile goes to the more substituted carbon. So that's like Markovnikov's rule that we talked about for hydration of alcohols before, or hydrohalogenation with HBr or HCl. So the selectivity is really the same thing. The electrophile on the end and the nucleophile toward the more substituted position. Now, bromine is especially corrosive reagent. Well, so is chlorine. And any of these reactions with chlorine or bromine can be hazardous. There's an alternative to this, and it's called NBS, N-bromosuccinimide. And N-bromosuccinimide looks like this. And you don't need to know, the name of this yet or where this comes from. This is succininic acid. This is the imide of it if you have a nitrogen there and you have a bromine here. Okay. And just remember the acronym, NBS, N-bromosuccinimide. At least know what the structure is. But what it's going to do here, if we take an alkene with NBS, and instead of drawing it out, you can just say NBS over the arrow, okay? And water. What are we going to get? Well, the bromine acts like electrophilic bromine, okay? That's what it is. So let's go ahead and attack and push the electrons toward nitrogen. This will give us a byproduct with a negative charge on nitrogen, which is resonance stabilized. Then that's a good thing in that case. But we'll get the same bromonium ion, Br plus, bridging both carbons. Right now we have NBS anion, and you can see that's resonance stabilized, okay? But yeah, we're still neutral overall charge. And then we're in water. So what are we going to do? We're going to open up like before, and we're going to get the bromo, hydronium ion. Okay. Now that's not the final product. Before we used water to deprotonate the hydronium ion, but look, we have a better base now, which is the succinimide anion. And that can take the proton off and give us the product, which is going to look like the same, okay? It's still a bromohydrin, a halohydrin, but we're not using bromine. We're using a more stable, well-behaved agent. This is a nice, non-toxic yellow solid material. You can weigh it out and it acts very well, whereas Br2 is very corrosive. It's volatile. It'll start to escape on the balance if you try to weigh it out, and it can be a pain to work with. But NBS, water, lets you do the halohydrin, exclusive for bromide, okay? We'll stick with that one, NBS for N-bromo, succinimide there. And I think that's it for that reaction. That's our fourth reaction. Halohydrin, check those mechanisms. It's really very similar with the bridged halonium ion. And then instead of halide anion attacking, we've got the water as our nucleophile for reaction 4 there. All right, let's do 5, which is what? It's going to be, let's see if we're keeping track of these. All the H reactions, right? We've got hydroboration now, okay? So hydroboration and boron. We're going to use a boron electrophile now. But I'm going to start this reaction by posing a question for you. Can we convert this alkene to the less substituted primary alcohol? And so far, the answer is no. If we use water and sulfuric acid, what will we get here? This is the reaction we know so far, right? Sulfuric acid and water going to that, the secondary alcohol. Okay, why? Because it's Markovnikov selectivity. The proton goes to the N carbon to give what? The secondary carbocation. That's the stable pathway, and then water attacks there. So hydroboration offers a way, a means, to provide the less substituted alcohol, okay? But we're going to change the electrophile now. It's going to be different, okay? So let's see what we got to do. We're going to take, instead of acid, we're going to take borane, BH3. Now that's like alkane when we talk about carbon hydrides, right? This is borane, BH3, and boron's just to the left of carbon in the periodic table, 3 valence electrons. So it has 3 hydrides, but it has an empty orbital right here. Why? Because even with the 3 bonds now being neutral, borane, it's what? It's coordinatively unsaturated. It only has 6 total electrons. Atoms in this area in the periodic table want to have what? They want to have the 8, okay, the octet rule. But it's going to get there, okay? Let's do this. That's our electrophile now, okay? With this empty orbital, it's electrophilic, and we're going to put that electrophile on the N carbon. And when we pull these electrons out and fill that orbital, look, that becomes borate. This is negatively charged. What about this carbon? If we pull the pi electrons out, that becomes a carbocation, right? Now verify these formal charges. Make sure you understand those. And look, we're forming the more stable, the more substituted carbocation intermediate. And we have borate with 3 hydrides on it. So what can we do? Let's just transfer or shift, and we've talked about shifts before, shift that over. And what are we going to get? We're going to get a new borane, okay, now stuck on carbon, okay? And so that's okay. To see the rest of this reaction and what we're going to do here, our next step is to dump in peroxide and base, okay? And that peroxide and base converts the borane, and we'll go over that mechanism. It converts it to the alcohol, okay? My whiteboard skills are kind of in need there. Primary alcohol. But we really did the same thing. Electrophile goes to the N carbon, more substitute carbocation, and then oxidize the carbon-boron bond. And I'll show you how that works. So there's 2 steps here. First, we add the borane, and then slash here means the second operation with the peroxide and the base to get the final product, okay? Now, to say something about this mechanism here, actually what occurs is this is known to be a concerted process. The alkene grabs the empty orbital at the same time as hydride migrates over. There's actually never a carbocation, but in this transition state, we have carbocation-like character, and this bigger boron atom wants to go to the end. So there's a couple reasons why we get this selectivity, okay? Even though we call this the anti-Markovnikov product, it's still putting the electrophile on the end there, okay? There's another thing we can talk about here, and that's this. We really only need 1/3 of an equivalent of borane. Why? What do you see after we add 1 alkene? We still have 2 hydrides on here. So what can occur here is we can add 2 more alkenes, okay? And those add there in such a way that we get the 2 butyl groups, extra butyl groups adding on there. And there they are. Now it goes from this monoalkyl borane to a trialkyl borane, okay? And then it's the same thing here with peroxide and base. Look, all of these, usually this is big excess for these. All of these then go to the primary alcohol, okay? So you can use either one there. This was developed by H.C. Brown at Purdue University in the 60s and 70s. It's a much more recent reaction. He won the Nobel Prize for it because he was able to switch the Markovnikov selectivity over to the less substituted alcohols. And he did a lot of other variation reactions with these alkyl boranes, did a lot of different things. But we'll just stick with the oxidation and how those are formed there. Let's do some examples. And we'll do a little bit on the mechanism of how we oxidize the borane product. So let's see, how about this one here? So borane, BH3, and then peroxide, okay, and base. Okay. So what will that alkene give? Okay. How about this alkene? So see if you can draw the products there. Same conditions there. Let's see. How about another one? How about if we have this alkene? Okay. Oh, and let's have one more. How about this alkene? Okay. So we got disubstituted alkene, disubstituted di, and tri. We just did mono, right? And borane will do all of these. So which side gets the boron? Right, the N side here, and right there will get the hydride. So we'd expect this product, that alcohol, primary alcohol, okay, with hydride addition there. Here it doesn't matter, that's symmetric, so we'll get cyclohexanol, okay. And then what about this? If you got a big terbutyl here and a smaller methyl here, yeah, think about it. The boron will prefer to be over here on the smaller side. Hydride will add right there. And eventually, what do you get? You get that alcohol, okay. Notice there's no migrations here. If this was a true free carbocation, you might expect migrations. But with borane, it's known to be this concerted thing, no carbocation. So no migration here. What about here? Let's see. We're going to get this alcohol, right? Because borane's going to go to the less substituted side, and then we're going to deliver the hydride right there. Now, those are the two groups that are added, right? Hydrogen and borane, which eventually becomes the alcohol. We've got some stereochemistry issues here. Is the hydrogen and the hydroxyl, the alcohol, going to be cis to each other together on the same side of the cyclohexane, or are they going to be across? So we need to look at that. Let's see. What's the mechanism here for this one? So we've got what? Got this boron, hydride, and the two other hydrogens there. But here it is adding here, and then hydride is concerted. It comes from the same face. We call that syn addition, okay? It's not anti like halogenation, where you got the bromonium or the chloronium ion top, and then bromide or water or whatever comes from the other side. Here, these both are on the same side, either both on the bottom or both on the top. Let's see, I drew them both on the bottom, right? So let's see what we get. That methyl will be up, hydrogen down, and borane is down. Okay. So what are we going to do? You see the boron and the hydrogen are cis right now. What does the peroxide and the base do? Let's see. Sodium hydroxide and peroxide. Let's see. Well, hydroxide can take off this hydrogen, and then this oxygen anion can enter into that empty orbital on boron. Okay? And we didn't do anything to the stereocenter right now, right? So we just have this, BH2 and peroxide. And what is boron now? Boron is negatively charged. Okay? So I'm showing you the result of that. So what can occur at this point? Well, boron is negatively charged, has a lot of electron density. And now you have an oxygen-oxygen single bond, which is very weak. So we're going to do a shift. We're going to do a 1-2 shift, and we're going to kick off hydroxide. What's that going to give us? Got that methyl group still up. That's where that hydrogen came on to start things out with, right? And if we migrate over, what are we going to have now? The oxygen is going to be bonded to this carbon. We still have the BH2 there, and we've got hydroxide coming off. Verify that that is the result of this migration. It's really just a 1-2 shift. This carbon from borate, the boron negative charge, over to the oxygen with loss of hydroxide. And, you know, hydroxide's a terrible leaving group, but we're under basic conditions. We have strong base here. So we've got this. In fact, what else can occur is hydroxide can go there. And let's draw that intermediate. So notice we're maintaining that stereochemistry through the whole thing. We've got B, H2, and OH on there. Look, we're negatively charged again. So what are we going to do at that point? Well, now we can add water. And I guess we've got to get rid of this. Our mechanism keeps going around and around here. Let's see, if we got water in there, that's a proton source. And this is borate. So we can take this pair of electrons and just put a proton on there in place of the boron. This will now be more stable because this oxygen has lone pairs that can enter into that empty orbital on boron. But what do we get? What's the final product here? The alcohol is right here, okay? And we've got boron hydroxide. In fact, we can oxidize the other hydrides on boron and make boric acid. That's your cleaning agent in your contact lenses to clean that boric acid. That's the inorganic byproduct. We don't worry about that now, but the stereochemistry is important. The OH and the hydride are still cis to each other. And that's because the original syn addition of borate to that. All right, so that's the whole mechanism. I've never put this oxidation mechanism on a test or a quiz, but you should notice that this alcohol retains, or retention of the stereochemistry of the original syn addition of the borane, okay? So it gives this methyl group and the OH, you see, are what? Trans to each other. The hydrogen and the OH are cis. And those are just designations on there, but it's really the trans product. The bigger methyl group and the OH in this case are a cross match. So look back through that, make sure you're okay on the mechanism. One more key thing here on hydroboration, and that has to do with selectivity. Now, I said it always gives the the less substituted alcohol product. But let's see. So here's a typical reaction with just borane, BH3, and then put in the oxidizing agent to convert the carbon-boron bond to the alcohol. And you will get major product. For this exact example, you get 70% primary. And look at this. You get also 30% of the secondary. Wow, so that's quite a bit. And that's because borane's a pretty small reagent. And these terminal alkenes that don't have anything else here, you're just differentiating between hydrogen and a primary alkyl group. The selectivity is not great, 7-3. You have to separate that by distillation, okay? The secondary alcohol will have a lower boiling point. You can separate it. The primary one, due to better hydrogen bonding, will have a higher boiling point. So you can separate. But there's a solution to this. Use what's called 9-BBN instead. 9-BBN. Sorry to give you another acronym, yet another reagent here. That stands for 9-borobicyclononane. And let's see what that reagent looks like. It looks like this. It's still a borane, BH, boron hydrogen bond, but it has this big bicyclic hydrocarbon thing here. There's actually 9 carbon. This is bicyclic there, so that's where the 1B is called. And at the 9 position, you have boron, okay? So know the structure and what it means, but It's still a boron hydride, but it's very bulky now. Okay, so what it's going to want to do is put that hydride out on the end. And let's just abbreviate the rest of 9BBN with two alkyl groups. There are these two alkyl groups here and here, right? Which make it very bulky. And we can do our concerted addition and then do our oxidation. And with 9BBN, look what you get. For this exact example, you get 99% primary to 1% secondary. Why? Why is it so much enhanced now? Now, for the purposes of our class, you can just use borane. And if you put the primary or less subtle alcohol, you'll get full credit. But understand that there are a lot of different borane reagents. This still has a borohydride that can add. You have to add a 1 equivalent in this case. It's more expensive. But if you want super high selectivity, with these simple type of terminal alkenes, that would be the reagent to use. Okay, but if you use just borane, BH3 will still give you full credit. Okay, but okay, how is 9BBN formed? This is kind of a neat reaction. You take borane with this guy, which is cyclooctadiene, or cod, not the fish, the cyclic diene, cyclooctadiene. And you react it with just 1 equivalent of borane, BH3. And look at that. You'll do 1 hydroboration here. I'll let you finish the mechanism. That will give you what? It'll give you this. Okay. And you'll still have that. Okay. And then you still have this, right? To add in and transfer another hydrogen there. And you'll go to that. Okay. And we'll leave it at that, I think. cod can be converted into 9BBN, or you can buy a solution of 9BBN from Aldrich. Doesn't matter, but that'll give you the higher selectivity. Okay, let's see. What else do we need to do here? Yeah, we did the mechanism of that. Let's look at some complementary reactions now. Let's begin to compare some of these H reactions. And let's do this one where we've got this possibility of what? Rearrangements, right? We got the tert-butyl over here and this monosubstituted alkene. Let's do sulfuric acid and water. What's the product there? And let's do borane and then peroxide and base. And by the way, you have to draw out peroxide and base each time. Don't just say oxidize or whatever. To cleanly convert it to the alcohol, you need peroxide and base. And you saw the mechanism there. Let's see, what do we get here? If we protonate, proton on the end, carbocation, we'll get a migration, right? And what product will we get finally? Yeah, we'll get the rearranged, the migration product. Make sure you can go through that. If you protonate here, secondary carbocation, and then shift over there, tertiary carbocation, and that's where water goes on. And then use another equivalent of water to take off the proton from hydronium. Make sure you can do that. But that's obviously rearranged, and the alcohol is going to a highly substituted position. But borane, remember, what? It gives the anti-Markovnikov product. It's still the same idea. The electrophile, which is not a proton in this case, the electrophiles both end up on the end, but now the peroxide and base oxidize to what? The primary alcohol. Okay. Now, wait a minute. What if we want to form this? The non-rearranged Markovnikov alcohol. Well, we can't do it with water and acid. That won't work. But there is a reaction called Oxymercuration. And I'll show you these reagents. It's not in your book, but sometimes this is on standardized tests, and it completes this complementary set of alcohol reactions from alkenes. Can we make the more substitute alcohol with branching with no rearrangement? And yeah, you can. You have to use a toxic reagent, mercury acetate. Those are two acetates on mercury. Mercury is a heavy metal. It's very toxic. This reaction's been phased out. There are alternatives to it, but this is still the standard one in older textbooks, and it persists on some things there. In the presence of water, and then you have to add sodium borohydride. And don't remember these reagents for our test. I might review it later for the final, but it shows you this complementary conditions here. Sodium acetate and water, and then sodium borohydride actually reduces the mercury, which goes to the end position. Mercury is actually the electrophile in this case, and you see water going to that position. And there's no carbocation here. Mercury is big enough to bridge over and to keep it from rearranging there. And then you have to add a hydride there from sodium borohydride to take the place of the mercury. And then you got to dispose of the mercury safely, which can be a challenge. Okay. I think that's enough there. Let's keep track of these reactions now. I want to do some mechanistic stuff and some multi-step stuff. Can we take this bromide and go to this alcohol? Yeah, we know a couple ways to do this, don't we? We know how to do that with water, just an SN1 type reaction, or hydroxide, with a secondary. That's okay. And we can go to that. And then do we know how to take that alcohol to the alkene? Well, we could take the bromide to the alkene as well, right? TB-toxide. That's what? Your E2 reaction. But we also know this now, right? Sulfuric acid and heat, right? That's from the earlier chapter, chapter 9, that dehydration now. Now we can also take this alcohol and convert it with tosyl chloride and pyridine to the tosylate. And then we've got a lot of possibilities, all those nucleophiles that we learned before in chapter 7, azide and acetate and amines, ammonia. We can substitute a lot of things here. In fact, we can do those reactions also via the bromide here. So we've got a lot of complementary relationships here between this. What about this type of reaction? Can we convert an alkene into a bromide, dibromide? Yeah, we just learned that, right? So if we have the trans one, we'll get the meso-dibromide. And then we can do a lot of stuff with that. We can convert that into, let's see, how about if we had 2 equivalents of sodium TB-toxide? Yeah, we'd go to the alkyne. And that'll be important here coming up in chapter 11. We'll see some other reactions. How about if we treat with bromine and water? What are we going to get here? Yeah, we're going to get the bromohydrin. So instead of bromide coming in, water is going to come in. Okay. And now at that point, we can actually treat with strong base, sodium hydride or sodium amide. And that will take the proton off the alcohol. And the bromide's right there still. And look, this becomes a nucleophile within the same molecule. You can do the backside attack there. And what do you get? You get the epoxide product. Okay. And that epoxide can be very useful for a lot of reactions as well. Let's look at a couple of these. So what can we do here? Let's make the bromohydrin from a terminal alkene here, maybe like that. Bromine and water. And we're going to get what? we're going to get alcohol and bromide. Okay. And notice I'm putting the alcohol at the more substitute spots because that's where more carbocation character will be. And then let's treat with sodium amide, strong base, which you're going to take the proton off and then form what? The epoxide. Not keeping track of the stereochemistry, it's DL at that point. You don't need to worry. And let's react this with an acetylene anion, maybe the potassium salt of acetylene. What's this going to do? Well, it's going to attack the epoxide. Remember, we did epoxide reactions before. We're going to open that up. We're going to have what? The alcohol will be O minus right now. And what? The acetylene will be right there. We just made that bond right there. Okay. And then we quench with water. That's a secondary step. And that will give us the alcohol and the acetylene. Okay. So there's a multi-step synthesis of this alcohol from this simple alkene via the reactive epoxide. Okay, that's a good one to keep in mind there. Let's see. Yeah, that's enough. And we'll do more of these synthesis type problems at the end of chapter 11 there. So I think that's pretty good for now. And when we start chapter 11 next time, we'll review all the reactions here from chapter 10. So we'll leave it there at that point. So very good. We'll see you next time. Make sure you get your homework 10.